Okay, so here they say the reaction between excess magnesium hydroxide, a slightly soluble base, and nitric acid occurs in aqueous solution where it produces magnesium nitrate, which is the salt. And this salt is actually soluble in water. And this is the balanced chemical equation. Okay. And this is important. They tell us that magnesium hydroxide is in excess. It is an excess reagent, which means that the nitric acid is the limiting reagent. Okay. Now they say to us 0.05 cubic decimeters of the magnesium hydroxide solution has a concentration of 0.115 mole per cubic decimeters. And this is added to 0.025 cubic decimeters of a 0.095 mole per cubic decimeter nitric acid solution. And now they're asking us to please find the pH of the final solution. So, well, this one, I know that you can perfectly execute it. You're now comfortable, or at least you should be comfortable with finding the pH of the final solution. Except that in this case, what is in excess is not an acid, but instead a base. So if a base is in excess, it means the base is the one that will determine the pH of the final solution. So it means we'll have to begin by finding pOH and then use the relationship between pH and pOH in order to get the pH of the solution. So what I want you to realize is they gave you information about both of your reactants that will enable you to determine which one is the limiting reagent. But we don't need to do that since we already know that magnesium hydroxide is the excess reagent. So we can use this 0.05 cubic decimeters and 0.115 mole per cubic decimeter to find the number of moles of magnesium hydroxide that are available at the start of the reaction. And then we can use this information about nitric acid, the volume and its concentration, to find the number of moles that reacted with magnesium hydroxide. So in other words, the number of moles of magnesium hydroxide that reacted, or those that were used to react with the acid. Then now that we know those that are available at the start, as well as those that are needed to react with the acid, then we can find those that are in excess. And now that we know the moles in excess, we can find the concentration of those moles in excess. Then we can find our pOH and then our pH. So yes, that's what we need to do. So let's go ahead and do it. So first things first, we want to find the number of moles of magnesium hydroxide that are available at the start of the reaction. But since we are given the concentration and the volume, then it makes perfect sense for us to define the concentration. So we know that concentration is defined as the number of moles divided by the volume. That is what we know. And we know that concentration is given to us as 0.115. We are looking for the moles, and the volume is already given in the correct unit. They said it's 0.05. Then now it's time for us to cross multiply. So these are the number of moles of magnesium hydroxide that are available at the start of the reaction. So when we say 0.115 times 0.05, yes, we simply get 0.00575, and then we say moles. All right? Well, that's nice. Now we come back and find the number of moles of nitric acid, because we understand that we can use them to find the moles of magnesium hydroxide. And since, once again, for this nitric acid, we are given the concentration and the volume, so it makes perfect sense for us to define the concentration of that solution. And the concentration of the acid here is given to us as 0.095. We are looking for the moles, and the volume of this solution is simply going to be 0.025. Okay. Then when we find the number of moles of the acid, we simply say 0.095 times 0.025. And when we do so, we simply get 0.002375 moles. Then we come to the mole ratio between this acid as well as the base. So we tell them that, well, according to the balanced chemical reaction, the relationship between magnesium hydroxide and nitric acid is actually a 1:2 relationship. So what does this mean? It means that if I have 0.002375 moles of the acid, then how many moles do I have for the base? Well, I simply take these moles of the acid and I divide them by 2. And of course, I can times this by 1. So this means the number of moles of the base will simply be half of that. So if we divide this by 2, we get 0.0011875. And then we say moles. So these are the moles that are needed in order to react with the acid. So now we know the moles that are available at the start of the reaction. We also know those that are needed to react with the base. So now we just need to find those that are in excess. Then we say, well, the number of moles of this base that are in excess. I'm not going to write the formula since you're now familiar with it, but you need to write it. But we'll just tell them it's those that we had at the start, which were 0.00 578, I suppose. Well, it's 575 actually, minus those that are needed or used to react with the acid. It's the ones that we just found. So it's 0.0011875. Then when you find the difference between those two, well, we find that 0.0045625 moles of the base are actually in excess. So now that we know the excess number of moles of the base, I don't just want you to go ahead and find the concentration of the hydroxide ions. You really need to be careful. You know, science is not kind if you're not careful, and small things, they really, really matter. What do I mean by that? I want you to carefully consider this magnesium hydroxide, all right? Now, when this magnesium hydroxide dissociates in water, I want you to see something that is important. Well, the space here is not enough, so we'll just need to go over. You don't need to write this reaction formally and show it, but you really need to understand. So if we look at magnesium hydroxide and we dissociate this, we dissolve this in water, well, we know that it's going to break up into its constituent ions. In other words, into the magnesium ions, which will be in aqueous solution. But a state here is not really important. And it's also going to form the hydroxide ions. But I want you to realize something that is very, very important. It's going to produce 2 moles of the hydroxide ions. Do you see that? It's very, very significant. If you remember well, sulfuric acid is a diprotic acid, and we know that it produces 2 moles of the hydronium ions when it dissolves in water. And as a result, the concentration of the hydronium ions is twice as much the concentration of the acid itself. Now, this will be the case for the concentration of the hydroxide ions. So now it's time for us to find the concentration of this base. So we know that, of course, it's going to be the number of moles divided by the volume. But how many moles are there? It's those ones that are in excess. So we have 0.0045625. And we divide this by the volume. It's the volume of what? The volume of the solution. Very important. And we know that in the solution, we have both magnesium hydroxide and the nitric acid. So the volume of magnesium hydroxide is 0.05, and the volume of nitric acid is given to us as 0.025. Very, very significant. Now, when you press this into your calculator, well, you simply find that the concentration of the magnesium hydroxide will be 0.060833. Well, it's so many threes, they are recurring. And then, of course, you'll have your mole per cubic decimeter. So now you come and tell us that the concentration of the hydroxide ions will be twice as much the concentration of the base itself. So in other words, it's going to be twice as much, 0.068. Oh, it's 0.8, 3, and so many threes there, such that when you times this by 2, you find that the concentration of the hydroxide ions will simply be 0.1216666. Well, it's so many sixes, but the last one is 7. And of course, it's mole per cubic decimeter. All right. Now that we know the concentration of the hydroxide ions, then we understand that pOH is the negative logarithm of the concentration of the hydroxide ions, which means it's the negative logarithm of 0.1216666 up until the last one, which is 7. But of course, you don't do those ellipses, you just write the entire thing. And if we now go to the calculator and find the negative logarithm of this, well, we can now take this to 2 decimal places. So we get 0.19. But what you found here is pOH. Then you state the relationship between pH and pOH. So you know that if you take the pOH and you add it to the pH, you get 14. Which means in order for you to find the pH, you just need to say 14 minus pOH. And you find that the pH of the solution will be 13.09. Yes, this is the pH of the solution. And it makes perfect sense because they told you that the base is in excess. And the pH that we are getting here is an indication of that, to say the final solution is basic or alkaline. Okay, so here they say to identify the metal M in an unknown metal carbonate,